Hey, welcome back. It's Sullivan again. I am back. Sorry to disappoint some of you. I was recently told by a student, not to name names, that you guys enjoy Mr. Kelly a lot better, and that is fine. I totally get it. I enjoy Mr. Kelly a lot better too. I will not divulge the name of the student who told me that. Imani Ways, that kid is right, and I don't want to, spoil who that was. All right, today we are in Module 3, Topic 2. We're going to talk about half-life and things like that. Exponential functions, very cool stuff. We're on page 561. I want to go down here real quick and talk about a few things. What is an arithmetic sequence and things like that? An arithmetic sequence is as follows. It's a sequence where you add from one term to the next the same thing. 1, 3, 5, 7. 2, 6, 10. I add 4 each time. Whenever I add the same thing from one step to the next step, that is an arithmetic sequence. What's a geometric sequence? Well, a geometric sequence is then when I am multiplying 2, 4, 8, 16. I'm multiplying by 2 here. All right. Whenever we have a constant multiplier, that is a good tip that we are a geometric sequencer. All right. And the last thing I want to review, this one is a very important. Let's say I have 4 to the x and I do 4 times 4 to the 7th. This is going to be important today. So when I multiply things with the same base, this is called the product rule of powers. I keep the base and I add the exponents, x plus 7. All right. So if I had 3 to the third times 3 to the negative 6, that would give me 3 to the negative third. 3 plus negative 6 is negative 3. Which brings up another rule here, exponents. Remember, negative exponents, generally, I always say the rhyme, if you want to change the sign, cross the fraction line. So a negative exponent takes it from where it was on the top, and takes it to the bottom. It becomes positive. We always have a 1 if there's not there, so that would be the same thing. All right, let's get into it. Let's go over to page 563 real quick. And we have a situation. Alice and Beth both receive $10 per week for doing chores for their neighbor. One day, Allison decides to increase her income using her knowledge of exponential growth. She proposes that her payment change to a penny for the first week and then double it each week after. So, Allison, let's go to Beth. Beth gets $10 every week. Flat rate. That's not bad for doing chores, right? All right. Allison income doubles every week. So the second week, she's going to make, whoa, 2 whole cents. Then she's going to make, whoa, 4 whole cents. All right. So what I want you to do now, take a minute, pause the video, complete this table and answer questions 2, 3, and 4 here at the bottom to the best of your ability. Don't worry. Maybe you just look at them and see what you understand. You definitely can complete this table though. All right. So go ahead and pause the video right now. All right. Welcome back. As you can see, here's our table. Maybe pause the video and check your values, but this I constantly multiplied every time by 2. That's my constant multiplier. Here, nothing really changes. She gets $10 every time. So how does Allison's income change as the number of weeks increases? So as the weeks increase, her income will double, right? Ooh, her income will double every week. Now, it doesn't look like much, does it? But it's doubling every week. At some point, that should be really good for her. Does Allison's income represent an arithmetic or a geometric? Well, remember, we talked at the beginning, geometric is when you have something and it is being multiplied by a constant multiplier. So that's why this is going to be geometric. And in general, a good form for a geometric is g sub n equals g sub 1, our first term, times some common multiplier to the n minus 1 power. All right? So in number 4, it says, write an equation to represent after n weeks. So the original term was, so g of n, this just means how much does she have after so many weeks, n weeks. Our first week, that would be 0.01, right? Times our common multiplier to the n minus 1. Our common multiplier this time was 2 because she doubled her salary. All right, so now what is the value of g sub n for n equals 0? So we know that g sub n equals 0.01 times 2 to the n minus 1. All right, so g sub n equals 0.01, 2 to the 0 minus 1. All right, so that's going to be 2 to the negative 1. All right, and when you multiply that out, you're going to find that that is 0.005, right? And that is actually smaller than our original, right? Because if you think about it, this would be week 0. This would be after 1 week, right? So this is like telling us how much she actually starts with. Does that make sense? This is like her starting value. And that's really important when we have functions, all right? This is a good sequence, all right? But this is a better function, okay? All right. Suppose the pattern continues. How many weeks would it take for her to have a greater weekly income than Beth? Well, we know that from our other table, week 8, we had 1.28. If we double that, week 9, we'd get 2.56. Week 10, we'd get 5.12. And week 11, boom, we'd get over $10 at 10.24. So it would take 11 weeks for us to do that. All right. Down here at the bottom, so this talks about the difference between an explicit formula and a geometric sequence and a function. All right, so the explicit formula we already came up with right here. Now we want to get this as a function in the terms of a b to the x. So something we start with, something we're multiplying, and just x. So if you look at this, we have a, b, but we have x minus 1. So here's how they do that. All right, first of all, you kind of did this up at the front. We know our starting value, right? Our starting value was 0.005. We found that for week 0. We found that. This is just a different way we could do that. So, all right. I'm going to come down here and look here. Everything is down here. We start in here. We're going to separate these two things. I'm multiplying, right? Think about going this way. I multiply. 2 times 2 is the same base. I add the exponents. N and negative 1 is n minus 1. I can then go this way and just do the same rule, but separating them. So I'm going to separate it 2 to the n and 2 to the negative first. So 2 to the negative first is 1/2, because we write it as a fraction. Negative sign crosses that fraction line. And then I can multiply 0.01 times 1/2, right? And that gives me 0.005 to the 2n. Now this is a function. Now we can find it for any week we want. All right, so if we want week 0, we can plug it in. If we want week 1, we can plug it in any week we want. All right, so what I want you to do is go to page 265 or 565, excuse me, and I want you to calculate the income that she earns per week given that formula. All right, so our formula again is 0.01 times, no, that's not it. It's 0.005 times 2 to the n. All right. So I want you to use that formula, all right, and figure out how much she earns each time. And then I want you to try number 8, all right? Pause the video and go ahead and do that. All right, so week 15, I plugged 15 in here, 0.005, 2 to the times 2 to the 15th, I got 163.84. Here I plugged in 20, I got $5,242.88. And 24, I got $83,886.08. You can see it is now going up much faster. And that kind of relates to this question number 8. All right, what are some characteristics of this graph? Well, we know that at 0, we started at 0.005. That was our starting value. All right. And we also know that as we go, these values are getting bigger really fast. All right, it's not a line. It's not going up the same every time. It's jumping incredibly fast, isn't it? All right. What I'd like you to do now is I'd like you to read the situation on page 556, or 566, excuse me, about Quentin and Alicia, and I would like you to fill out the table and draw any picture you can. All right? Go for it. All right, so Quentin starts with $1, and so does Alicia. So that's our starting values. We need to remember that. All right? And each week, he asks for 50% more. So really, what am I multiplying? I have 100%, and he's asking for 50% more. So I'm actually getting 150% of what I had the week before. So my multiplier is actually going to be 1.5. That's what I'm going to multiply each time. All right, so then you can see that's what I did here. I multiplied each value by 1.5. I kept the decimals, but rounded here for dollars and cents. All right. Over here, Alicia starts with $1, and she gets $1 more each week. All right, at the beginning, it looks great for Alicia, but as you can see, green is Alicia. Her plan kind of flattens out. Well, Quentin's plan takes off. So in the long run, you can see Quentin is going to earn much more than Alicia. All right, you can even see it down here on the table. After about week 3, Quentin is already earning more than Alicia. Then it says write functions to represent Quentin's plan. So Quentin, Q of x. All right, let's see. Remember, a times b to the x. A is my initial value. What is my initial value here? $1 times what is my common ratio? What am I multiplying by? 1.5 to the x. All right. I don't have to worry about any x minus 1 because I have my initial value, my value when x is 0. All right. Let's do Alicia's plan. Alicia has a linear model, right? So that's mx plus b. So what is her change in every week? $1 for every week, plus her initial value is $1 as well. So now we have our two functions, all right? All right, so I want you to look at page 567, take a minute, and answer these questions on your own on page 567, all right? And then we will talk about them in just 1 minute. All right, so if we look at question 1 to determine how much Beth earns in week 10. So if we use the Quinton method, 1 times 1.5 to the 10th power, she'd make $57.67. All right, and if we use the Allison model, or Alicia model, she would use 10 plus 1, or $11. So Beth probably should use the Quinton method, right? All right, suppose that Beth and Allison both start using their exponential model. So Beth has the Quinton model, $1 starting, times 1.5 constant multiplier to the 12 weeks. And Allison has the original one, 0.005 times 2, doubling it to the 12th. So let's talk about this. A couple of things. Our initial values, $1 and 0.005 cents. That's really low, much better, higher over here. Our rate that we're multiplying by, 1.5 and 2. So Allison has a higher rate, but Beth has a higher starting value, which gives her the edge right here, $1.20 or $129.75 versus Allison, $20.48. All right. Here it says let's use some technology to see when they're equal. So let's do it. Get your calculator. Plug these into y1 and y2. Pause the video to do that. All right. Let's go to our screen. Let's graph those out. All right, now you can see we have two things we can't see. So I need to change my window. All right, I'm going to change my window. I don't know. Let's see. Let's maybe make it 100. All right. Actually, let's go to my table and see when we can get them closely equal. All right, so I'm looking over here. 655, 5,000. Oh, somewhere in here, they're equal, aren't they? Between 18 and 19. So I'm going to go to 20 is my x, and I'm going to say 3,000 is my y. So my x is going to be 20, and my y, my max y is going to be 3,000. All right, let's graph that. And we can see they cross here. So if you remember how to find that, we're going to calculate that. I'm going to do second calc. I'm going to find out where they intersect, number 5. First curve, yep, press enter. Second curve, press enter. Do I want to guess? Sure, I go ahead and guess, and that's where I get my intersection. So 18.4 weeks at about $1,750. So I'm going to put about 18 weeks is when they will connect. All right, does it make sense in the problem situation? Well, it was 18.4, right? So we can't really do that. So they're never going to actually be exactly the same because they don't get paid in these. So they get paid at 18 weeks, they get paid at 19 weeks. So it doesn't really make sense at 18.4 in this situation, does it? All right, let's compare Allison and Beth's function models. As the number of weeks increase, whose model will generate more per week? Well, let's go and look at it, right? So this is Allison is y2. Let's look at our table of values. As the weeks increase, you can see y2 eventually takes over. Y2 eventually takes over in the long run and will make more money. All right, so that is Allison, I believe, correct? Yep. All right. And I believe that's because her rate was 2 as opposed to the other rate, which was 1.5. This is going to help you out generate more money faster, even if you started with a lower initial value. So considering the A and B values, how did that support your claim? All right, so again, so the rate of 2 in the long run helped us get that up higher. Now initially, our A value for Beth was higher, was 1 versus our A value here, right? So let's look at our formulas. We had q of x equaled 1 times 1.5 to the x, and we had g of x equaled 0.005 times 2 to the x. So initially, the higher initial value was better. But in the long run, this rate of doubling it made it much better. Okay? Please take a minute and read this situation on page 568 about caffeine, and do your best to complete this table all by yourself. See how you do, all right? All right, in this situation, we start with a certain amount of caffeine, and we're talking about its half-life. Half-life is very important. All right, so its half-life is every 5 hours. Not every hour, it's every 5 hours, and that changes things just a little bit, all right? So when it talks about how much caffeine remains in his simian system after 5 hours, that's half, because 5 hours occurred, so half of what he had, so that would be 40 milligrams were left in his system after 5 hours. Now, another 5 hours, so half of that would be 20 milligrams, right? I'm multiplying every time by 1/2. So my constant multiplier now is a half. So if we look at it, the table, 1 half-life cycle, right? I had 80, then I had 40. 2 half-life cycles, I'm down to 20. 3 half-life cycles, I'm at 10. 4 half-life cycles, I'm at 5. All right? So what is the total? What is the initial amount? His initial amount is 80. So we think about it in terms of our equation. This is our general form equation. Our initial value is always at A value. The B value is always our rate. What is the rate of decay? Well, it's 1/2, but it's not to the x, because this half happens every 5 hours. So I have to put that divide by 5. I only want to do the half when that number of hours reaches 5 or 10 or 15, because 5 over 5, that would be 1 half-life cycle. 10 over 5 would be 2 half-life cycles, and so on. So when I have half-life, often as this occurs, it says it happens every so many cycles, or minutes, or years, or in this case, hours. All right? So take a look on page 570. All right, we're going to use technology to predict when the caffeine is completely out of the system. All right, does it make sense? So I want you to put the equation into the calculator and look at the table and see how long it's going to take for it to be completely out of the system. So go ahead and pause the video right now. All right, so the questions ask, when is it completely out of the system? So I put it in here. I'm going to go to my table, second table. I want to look to see when it hits 0, when it crossed over to 0. So I'm already at 18. Now you can see it's decreasing by half every time. And it gets real close to 0, right? Is it ever going to get to 0? There is no way it's ever going to get to 0, is it? Because when I take a half of something, it's always getting closer to 0. I'm halfway closer to 0. I'm halfway closer to 0. I'm halfway closer to 0. But I'll never actually get to 0. All right, so for number 7, we'll never actually get to 0 with this model. Now, does that make sense in the real world? Well, probably if he never drank caffeine again, at some point his body would say he has no caffeine in him, right? So we have to be very careful about that thing. All right. So when is it going to equal 1 milligram? All right, let's take a look. So 1 milligram, let's go to y equals, and we wanted to know when it equals 1. Let's use this technology. Let's graph it. So I have it way over here. Now I already changed my window to like 35, I think, or something like that. So let's see where they are. I'm going to calculate second calc. I want to find out where they intersect. Where do they intersect? They intersect, there's the first curve, second curve, and guess they intersect at 31.6. So approximately when are they going to be the same? At about 31.6 hours, there will be 1 milligram of caffeine left in his system, all right? Use the properties of powers to rewrite the function so that only the variable t is in the exponent. All right, so we're going to change it to x. All right, so we started with 80. And what they're saying is this. So we had 1/2 to the x. They're saying t over 5. All right, so now I want you to remember a few rules. If I had this, 2, 4 to the x, an exponent to an exponent, I could write that as 4 to the x. All right, so I'm going to rewrite this as 80 times 1/2 to the 1/5 times x. So now I can do all of this by itself. So I want to put in my calculator 1/2 to the 1/5. When you put that in your calculator, you're going to get about 0.87 with some other decimals. So now we have a formula that is our half-life formula, right? But our half-life was only every 5 hours. So this actually tells us how much it decays every hour. How much does it decay every hour? Well, if we start at 100% and we're at 87%, that means that each hour it decays about 13%. All right, so it's going to decay about 13% each hour. Now that's 13% of what it had before. See, I can't just take 50, I can't take my 5 hours and divide by half and see what I get. Each hour I'm going to learn 13% of what I had in my system at that time. All right? All right, I just want to wrap a few things up here because, we did a lot of situations, but sometimes we didn't talk about everything we need to talk about, I don't think. This is the general form of an exponential functions. And the a value is always my starting value or my initial value, all right? It's what we have when time is 0, all right? T equals 0, like what we start with, all right? And this is always going to be our rate, all right? We're going to have growth when that rate is greater than 1. All right, we're going to have decay when that value is between 0 and 1. All right, sometimes we're going to be told that we had a 2.5% increase. And you have to remember that 2.5%, we started 100% plus the 2.5%, so that would be 102.5%. That would be the percent we use. The decimal we would use is 1.025. If we had a 2.5% decrease, we would do 100 minus 2.5, right? And we get 97.5% or 0.975. Just some things I want you to understand, because when we get into these situations, they're not that hard to set up if you know the initial value and you know your rate, okay? Your classwork is right here, all right? I do have some extra work if you practice problems if you'd like them, though. Just don't hesitate to ask. And as Mr. Kelly always says, it is important to be nice, but it is nice to be important. I think that's what he says. All right, good luck.